Another way of improving on Euler's method for integrating ordinary differential equations is a method called the midpoint method. Again, we did this in Eng 1060, so I will go through this reasonably quickly. The midpoint method is a different way of improving on Euler's method compared to Hoyne's method. With Euler's method, what we're trying to do is to estimate the slope at the midpoint of our interval. So we're going to use the nomenclature, an index of I plus a half, to represent a point that lies between ti and ti plus 1. We're still going to use the notation that the distance between ti and ti plus 1 is equal to h. The midpoint method is also a predictor-corrector method, just like Hoyne's method. So let's look at the steps we need to find the solution yi plus 1 when we already know yi. So our aim is to estimate the slope at the midpoint, in other words at the point ti plus half yi plus half, and substitute that into the right-hand side function. The problem is we don't know what yi plus half is. It's something we need to try and estimate. So we know ti plus half is just equal to ti plus h on 2. So let's estimate yi plus half using an Euler step, but this time we're going to choose a step size of only h on 2. We're going to do a half step. So if we start at the initial point, ti yi, calculate the slope, do a regular old Euler step with a step size of h on 2, we can come up with an estimate of yi plus half. It's just given by this formula here. yi plus half is equal to yi plus h on 2 times f of tiyi. So there's nothing different to Euler step except we've chosen a smaller step size. We now need to approximate the slope at the midpoint by substituting ti plus half and yi plus half into our right-hand side function. That gives us the blue vector there for the slope. And finally, we use that slope to take an entire step, h, to find the solution at time is equal to ti plus 1. So we go back to the beginning of the step, and we say that yi plus 1 is equal to yi plus h times the slope at the midpoint. So that then gives us our value of yi plus 1. That is the midpoint method. It's sometimes called the improved Euler method. So the predictor step is yi plus half is equal to yi plus h on 2 times the function value at the initial point, ti yi. So we calculate that just using an Euler step with a step size of h on 2. The corrector step then uses that slope to do a full Euler step from the initial point. That's the corrector step. Graphically, what we're doing is here, we're starting off at the point ti. We're going to the halfway point as the predictor, and then the corrector, we take that slope at the halfway point and do a full step from the beginning. Multiple steps of the midpoint method progress exactly as with Hoyne's method. So we've just, up the top there, we have the formula for the midpoint method. We start with our initial condition t0, y0. We perform an Euler step with a step size of h on 2, and I is equal to 0 in this formula at the top here. That means that y1 half is equal to y0 plus h on 2 times the function evaluated at t0, y0. We then calculate the slope at t1 half, y1 half. And we calculate y1 using this slope using the corrector formula, which is that formula down there, with I is equal to 1. I is equal to 0. So we've now done one step of the midpoint method. We've got t1, y1. We want to calculate t2, y2. Perform an Euler step with a step size of h on 2 and I is equal to 1. It gives us y 3 halves. That's the midpoint of the next interval. We calculate the slope at this midpoint. It's only an estimate, but it's a reasonable estimate. And then we use that slope to calculate a full step using the corrector formula down here. So y2 is equal to y1 plus h times the function value evaluated at t3 halves, y3 halves. And so on we go for I is equal to 2, 3, 4, etc. Again, this is easy to code up into MATLAB, but you just put this inside a loop. Typically it would be for I goes from 0 to the number of steps that we want to take. As in Hoyne's method, it's possible to show that the error when integrating from ti to ti plus h in a single step using the midpoint method again scales like h cubed. That's the most important thing to recognize. This is the error in a single step, so halving the step size means 8 times smaller error, again, which is more accurate than Euler's method. And again, using similar arguments to those used with Euler's method, the global error in the midpoint method can be shown to be equal to order h squared. So again, it's more accurate than Euler's method, and it has a similar degree of accuracy to Hoyne's method. Formally, they have the same order of error. In practice, of course, the actual errors will depend on exactly what equations are being integrated.